This video is taking a look at linear approximation and differentials. This example is mainly going to compare the differences between what delta x and delta y represent and what the differentials dy and the other differential dx, what those two quantities represent. So we have an example here. We're given a cubic function, and we're talking about the specific point when x is 1, and that delta x is 0.5. So let's talk about delta x and delta y first. Delta x and delta y have to do with the function, the specific function. So part A says compute delta y, and we're going to skip this for now, we'll come back to that. Compute delta y for the given values of x and delta x. Okay. So on this function, when x is 1, plug in a 1, y will also be 1. And since delta x and delta y have to do with this function, let's see what happens here. When delta x is 0.5, so the change in x is going to be 0.5. Let's change this x value by 0.5. So what happens to the y value? I'm going to now put in 1.5 into x cubed. So this is going to be 1.5 cubed, which is 3.375. So when delta x is 0.5, what is delta y? That looks like that changed 2.375. Alright, so let's take a look at that on this graph here. What we just predicted was that if x changes by 0.5, y will change by 3.375. So here's the point 1, 1. Notice that the scales here are quite different in terms of x and y scales. And we're saying when x changes by 0.5, so I'm watching, here's 1, here's 1.5. Right here. This segment represents delta x. Okay, so on that function, when x changes by 0.5, what's y going to do? So when this is 0.5, so on the y value, we're going from 1 up to this point right here, which you can see is almost 3.5. Here's 3.5, almost 3.5. We know it's going to be 3.375. So delta y right here is 2.375. It went from 1 up to 3.375. All right. Let's take a look at dy and dx. So if we're dealing with y equals x cubed, we know that dy dx is going to be 3x squared, and when we solve it for the differential dy, that will equal 3x squared dx. So if we want to compute dy, we're going to take 3 times our x value of 1, square it, and then multiply it by dx. And notice in the directions here it says when dx is the same as delta x. So since delta x is 0.5, dx is also going to be 0.5. And so dy at that particular moment is going to be 3 times 1/2, or 1.5. So let's take a look how that applies on our graph here. So we know that dy dx represents the slope of the tangent line. So that's what I'm going to do here. When x is 1, I'm going to take a look at, I'm going to draw my best, I'm going to eyeball it, draw my best tangent line here. Looks something like this, I would say. So let's get this tangent line here. So there's a pretty good tangent line. Notice it's just nicking right there at that point of tangency. And so on this tangent line, when dy is or I'm sorry, dx is 0.5. So we get out to this point. How far is it up to here? We computed that it's 1.5. So I'm going to actually keep it color coordinated here. I'm going to do some brackets here. So when this dx is 0.5, what is dy? We computed dy to be 1.5. And so that would be the comparison of delta x and delta y, which is on the function, and then dy and dx, which is on the tangent line.